When I first started teaching this class about 15 years ago, I actually had to do a lot of introduction to a lecture on climate change. And I feel like that's kind of not the case anymore. I feel like you have, as students, grown up with the reality of climate change. You've heard about it probably since the first day you were in school. And so I think it's kind of more important to talk not only about things like, greenhouse effect, greenhouse gases, climate change, and whatever, but for a class like this, where we're talking about kind of change over time, I want to give you a little bit of the historical perspective and discuss the idea that climate change can have natural causes, absolutely. And in fact, throughout Earth history, we have seen many examples of dramatic, rapid climate change. And then kind of though relate that to, is that what's happening right now? Do we see it as a natural phenomenon? Is it actually then driven by humans, or is there a combination of both? So this is actually just a graphic that a colleague of mine from Rutgers University made. And it's the Statue of Liberty essentially up to her armpits in seawater. But this is the scenario that would happen if all ice on land across the globe melted. So what you would have is about 70 meters of sea level rise. So at least in the movie The Day After Tomorrow, this is something that they got right. There would be about 70 meters of sea level rise. And so Manhattan, right here's New York City, in the background would be flooded. But also then, yeah, you'd see the Statue of Liberty covered mostly by about 70 meters of increase in sea level. Just like we've been talking about the lasting effects of waste disposal, so things like nuclear waste and whatever, this is actually a cartoon that was published a couple of years ago. And we talk about radioactive waste and the damage that radioactive waste can do. But if you notice too that this is a kind of a cartoon where you're seeing that actually it's the waste that we don't see, right? It's the byproducts of burning things like coal, oil, and gas that we actually don't necessarily see because they're not solid, but those gases, the CO2 and the methane that we produce by burning fossil fuels, we don't have a place to necessarily put them, right? Because they're not solids, and so we don't have to store them like nuclear waste. But where do they go? They go, of course, into the atmosphere, and we're seeing the effects of increases in some of those gases. So just to kind of throw some facts at you, and remember, these are not something that you have to memorize, but I do kind of want to show you scales, right? So it wouldn't be important necessarily to know that over the past 100 years, global temperatures have increased, 1.9 degrees, but notice that the scale, right? Essentially over the past 100 years, over the past century, you've had, 1 to 2 degrees of temperature change. And what I've tried to do here is I've tried to convert stuff from centigrade into Fahrenheit, but, sometimes we have to be a little bit flexible with that. But we know that now global temperatures are increasing. So over the past century or so, 1 to 2 degrees Fahrenheit change in global temperature. So much so that now we've actually even got the IPCC report, right? The Intergovernmental Panel on Climate Change has now actually said that the scientific evidence for warming of the Earth's climate system is now unequivocal, excuse me. So with that increase in global temperature, we've also seen that sea levels are going up, right? On the order of millimeters per year, but if you put that together, right, that's about 1 inch per every 7 years, right? So every decade or so, you're seeing a little over an inch in sea level rise. Again, I don't need you to actually memorize, right, these, 3.3 millimeters or whatever, but put this into scales, right? 1 to 2 degrees Fahrenheit per century, and, about an inch per, 10 years or so, or maybe greater than an inch per 10 years or so. We know too that now the data show that polar ice and glacial ice throughout the world is decreasing. In two or 3 years ago, when I made this PowerPoint, it was only about 125 gigatons of ice were being lost per year. I had to change that last year to now update it to notice almost like a 4-fold increase, right? Now you're up to over 400 gigatons of ice are being melted per year. You also might notice that weather patterns are certainly changing, right? We're actually seeing an increase in the magnitude and frequency of large storms, not only here on the Atlantic coast, but then also typhoons and things in the Pacific. So since about 1970, since we've been measuring the magnitude and frequency of really big storms, we've seen an increase in both the duration and the intensity by about 50%. So the data do show that climate has definitely changed, and things are certainly getting warmer, sea level is rising, ice is melting, and we're seeing changes in weather patterns throughout the globe. I feel like every year I do this PowerPoint, right? We kind of see these records. And in fact, I think we're already seeing the news for 2020. But here, 16 of the hottest years on record. And we've been measuring the temperature record for 136 years. 16 of the 17 hottest years have been since 2001. So if you look at the data here, right, this is a temperature anomaly. So this is a difference in temperature, right? So these are temperatures that are slightly cooler. But notice that actually, as we go towards the year 2020, we've seen temperatures gradually increasing. And I feel like every year, right, there's a new media release. So here's, data released in 2014 shows that May's temperatures were the hottest on record. Then I had to update it. Wait a minute, in 2015, the first 5 months of 2015 were the hottest on record. Oop, then I had to change it again in 2016. Whoops, the hottest year so far, right? There's the 2016 data. Oh, wait, nope, I lied. There's 2017, right? Here's the third hottest year on record, the hottest year without an El Nino. So it seems like, every year we're getting now these new records of hottest temperatures. Here's the 2018, right? Global temperatures, fourth hottest year on record. And then I even found, here's some of the data from 2019. Here's the temperature anomalies that were from last year. And of course, we're still kind of in the middle of 2020, so I don't really have a whole lot of good data there. But here's the first quarter of 2019. And that, while we are talking about temperatures on average getting warmer, are there places that are recording record warmth? Absolutely. Notice over here, right, you've got locations in the southeast and of course in the desert southwest over here that are recording relatively warm temperatures, right, even though we're kind of going out of winter into spring. But this idea now of kind of, we've abandoned global warming and instead started to call things climate change, because does it mean that everywhere on record is getting warmer? No. And in fact, if you look at this area right up in here, you'll notice that for the first part of 2019, right, they actually had record cold temperatures. So just because we're seeing an average global increase in temperature over, 10 years, 100 years, doesn't mean that every place is getting warmer. In fact, some places are actually getting colder. So that's why we've kind of started adopting the term climate change instead of global warming, because climate is changing everywhere, but it doesn't always have to just be an increase in warmth. What are the implications of temperature rise? Okay, I'm going to kind of go through each of these on the next couple of slides, but you can imagine that as the temperatures do change, and especially when you get warmer temperatures, we're going to see a change in the length and the timing of the growing season. This has really big implications for certain crops that we're trying to grow because, right, certain crops, especially citrus fruits and things like that, actually need a spring frost in order to kind of produce their fruiting bodies. So really important for agriculture there that as temperatures rise, we may have frost-free days that actually inhibit the growth of certain fruits. Weather patterns, of course, are also going to change. As temperatures increase, you might see more drought in certain areas, but when temperatures warm, so do the oceans. And then warmer oceans means more evaporations. And in the tropics, that actually means the spurring of more storms, so things like hurricanes. You also, of course, will see ice melting with an increase in temperature. And as the ice melts, where does all that ice and meltwater go? Well, it goes into the ocean, right? So you'll see sea level rise, but you'll also then too see a loss in the amount of ice cover on the planet. Ice is actually great because it reflects sunlight, right? And so if you have an ice sheet and it's a bright white color, it will reflect sunlight and actually keep the planet cool. When you melt that ice and now you have a dark colored surface, that will actually absorb sunlight and actually aids in warming the planet. So melting ice actually exacerbates the problem of warming temperatures. So let's look at this idea of now kind of, temperature change and weather pattern changes. This is observed precipitation changes. In some places, we said, right, that weather patterns with warmer temperatures are going to cause drought. So you notice that in some areas, right, here's a kind of drought area, but that other areas may actually see a increase in the amount of precipitation. And so sure, we're seeing an increase in precipitation in some areas, right? But we also kind of are seeing then there's a regional change in the types of precipitation patterns caused by the increases in temperature. I mean, how often have we been hearing in the last couple of years about droughts in California and droughts in the desert Southwest, right? It's quite often. But then, of course, you're also hearing about flooding in the upper Midwest, and of course, then too, right in the Mississippi River Valley area. Where we do have areas of drought, they certainly affect agriculture. Certain crops that we grow in the Midwest, what we call, or the breadbasket of the US, certain crops are extremely water intensive, and corn happens to be one of those. So as drought starts to become a bigger and bigger problem in places where corn is a big agricultural product, we're going to see decreases in the amount of corn that is produced or that is able to survive. And therefore, certain prices are going to go up. Now, think about this. It's not just the price of an ear of corn. What else are you going to see are going to go up? Don't forget, we use corn for a ton of stuff. One of the big things, believe it or not, is that you're going to see corn syrup go up in price. And what's the main user of corn syrup? Things like Pepsi and Coke and most of the sweetened cereals and everything like that. So prices for things like soda might start to go up. We also use corn as an additive in our gas, right? Because corn is used to make ethanol. So you'll also see gas prices start to go up. Here's another thing that you might not notice too. The prices of beef are going to go up because, believe it or not, on feedlots, beef cattle are fed a ton of corn to help them gain weight very quickly. And so if there's less corn to feed the cattle, you'll also see too that beef prices are going to start to go up. Here's an interesting little article from a couple years ago from Scientific American about how with drought and corn prices going up, it actually hit the Pepsi Cola market quite significantly. So take a minute and I want you to kind of watch this video link here. Go to this Vimeo link and I want you to watch. It's a quick, 3-minute video. But essentially I want you to watch that video because it actually shows the implication of drought with not only agriculture, but also too the idea that many communities rely on snowmelt for their city's water supply. So as temperatures get warmer, not only are we going to have problems with crops, but we also are going to have problems with fresh water availability, especially for those communities that depend on snowpack that is built up in the winters and then melts in the spring to kind of refill their reservoirs. So go ahead and kind of take a minute, pause this video here, go watch this Vimeo link, and then come on back when you're done and we'll talk about some of the key points of that video. So one thing that you noticed in that Vimeo video is that the implication of warmer temperatures means that the growing seasons are actually going to change, not only their timing when they start, but also the length. Here's a big thing to think about, right? Notice that over here on the West Coast, this is the increase, right? The increase in frost-free season lengths. You're talking about, half a month of increased frost-free seasons. And while that may sound good, right? Like, oh, great, we don't have frost, right? We don't have cold temperatures. We should be able to grow more. For some crops, that's a good thing, but for some things, especially citrus fruits, that's actually a really bad thing. Those citrus fruits need spring frost in order to get their flowers and stuff to start to produce fruit. So you're going to see an increase now in the price and the availability of certain citrus fruits as we have higher temperatures and shorter frost seasons. I just downloaded this map this morning, right? This is actually, I downloaded it. This is the recent data. And so this is showing areas across the US, continental and marginal, right? Because it's also showing there's Alaska, right? Here's Puerto Rico and Hawaii. This is showing the state of drought across the US. And the S's and the L's here are showing you short-term droughts, right? So the areas that are labeled with an S are short-term droughts. And the areas labeled with L are the long-term droughts. So you'll notice that there are regions, right, where you're seeing long-term droughts. And then, of course, the hotter the color is, right, the more red, the more severe the drought is currently. So we do have quite a bit of drought happening right now in the western part of the US. Puerto Rico is also dealing with quite a bit of drought at the moment. But if you think about it, pretty much, right, everything to the west of the Mississippi River Valley is pretty significantly under drought conditions. This is where we grow a lot of our crops, right? So this is going to have significant impact on this year's food production. It also will increase the risk of wildfires. I feel like every year, right, we kind of hear about wildfires in this region up here. So we will be watching for that as the summer temperatures increase. You're also going to see kind of meager, like weak snowpack. And of course, you might also see too, in some areas, you're going to start to have water restrictions. My grandmother actually used to live here in New Mexico, and every year they would have water restrictions. So certainly something to kind of keep an eye on as we go through the summer, see how things continue with the drought in the western part of the country right now. We also said too that with increased temperatures, not only are we going to see changes in agriculture and growing seasons and whatever, but we also said that we're going to see melting of ice and therefore the resulting increase in sea level. Here's just data right from NASA. Here's both of our NASA maps right here showing essentially mass in gigatons of ice for Greenland as well as Antarctica. And again, you don't have to recognize the numbers here, but hopefully you're just noticing the general trends of the amounts of gigaton of ice in both the Greenland and Antarctic ice sheets. These are the two biggest ice sheets that we have on land on Earth right now, have seen significant decrease since about 2002 or 2004. So ice is melting. And of course, the result of that is that sea level, therefore, is rising. Remember, we talked about this too. Sea ice melting isn't going to affect the amount of sea level rise. It's the melting of continental, right? So melting, how about I put here, continental ice, right? That's the important part. And so these continental ice sheets that we're talking about are things like Greenland and the Antarctic. So those are the ones that we're really worried about, right? And melting of those two ice sheets, of course, is showing that since about 1880 up to about present times, we are seeing a cumulative sea level increase on the order of several inches, right, since 1880 as we move up into current times. And that's most of that is from melting of the continental ice sheets. If we map sea level changes just around the United States, what you'll notice is that most gauges on the coastline of the United States are actually showing this increase, right, in sea level from about 1880, right, on the order of, 6 to 8 inches over the last, say, century or so. Actually, this is just showing from 1960. So we're showing increases in sea level around the East Coast, especially of the U.S., on pretty significant, 5 to 6 to 8 inches. Things are looking a little bit different if you look at Alaska. And so notice that Alaska is actually showing a drop in sea level. Now this is maybe a little bit strange, but just remember Alaska used to be under a huge amount of ice, right? And that ice was weighing down the Alaskan landmass. As we start to now erase, right, and melt some of that ice, the actual land surface of Alaska is starting to pop back up. And what that means is it looks like sea level around Alaska is falling, but that's not actually happening. What's actually happening is that Alaska is popping up. The actual land surface in Alaska is popping up, and it's just popping up at a rate faster than sea level is rising. And so it looks like sea level is dropping around Alaska. Let me try something here. Nope, okay, it's not going to work. Okay, so why is global temperature changing? What's going on? If we think about it, right, has Earth's temperature changed in the past? Absolutely. How does it do that? Well, if we think about it, generally speaking, Earth's temperature, right, the average global temperature is kind of a balancing act between how much energy from the sun is coming in and how much is going out. This is just a general flux, right? Input versus output. That's all we have to think about. So when the Earth has gotten more energy from the sun, it gets warmer. If the Earth is either reflecting a lot of solar energy, or if a lot of solar energy leaves the Earth, then the planet actually cools. So we have a decrease in temperature. So that's just this basic flux of how much energy is coming in versus how much is going out. So what can actually alter the energy budget that is found on the planet? The one that we hear about a lot is, of course, right, the amount of greenhouse gases. Now, greenhouse gases are natural, of course. Have they changed in the past? Absolutely. They're one thing that can alter the energy balance of the planet. Can we have a change in the amount of solar energy reaching the Earth? Essentially, can the sun change how much solar energy it puts out? Yes, and it has in the past. So let's investigate that. We can also then check on Earth's reflectivity, essentially the property of the planet to maybe reflect a lot of the sunlight that is coming in versus absorbing it. So all three of these things, right? Greenhouse gases, the change in solar energy, and the change in reflectivity, all of these things can alter the energy balance. So let's look at how we do each of these things and maybe attempt to figure out how much of an effect each of these is having on current climate change. Okay, climate changes over geologic time. We know this. This is data taken here from NOAA, right, the National Ocean and Atmospheric Administration. And notice the scale here, 800,000 years ago to present. And so we can look at the amount of, right, carbon dioxide in the atmosphere. And of course, carbon dioxide is a greenhouse gas, so that can be a way that we can interpret or infer temperature changes. What we notice that over the last 800,000 years or so is that we've seen kind of these cyclic fluxes, right, cycled changes in temperature and CO2 about on every 100,000 years, right? And if you remember from the Milankovitch cycles we talked about, that seems to be kind of, a natural cycle, and it's the change in the shape of the Earth's orbit around the sun. So climate does change over geologic history. And so if we look at the changes that we've seen in carbon dioxide in the past, we notice that the highest concentration of CO2 in the last 800,000 years is on the order of 300, and ppm stands for parts per million. You may be asking, how do we know this, right? How do we know how much CO2 was in the atmosphere 800,000 years ago? I'm glad you asked. Well, it has to do with this. Do you see that this person is now holding a slab of ice, and in that slab of ice there are a bunch of frozen gas bubbles? So in those frozen gas bubbles are atmospheric air pockets that essentially we can extricate, we can take that gas out of the ice and measure the amounts of different types of gases in Earth's atmosphere. Do we have ice that's 800,000 years old? Well, we have ice that's a couple 100,000 years old, absolutely. We have drilled ice cores, right, in the Greenland ice sheet and in Antarctica, and we've been able to pull out those gas bubbles from that frozen ancient ice, and we've been able to measure the amount of CO2, methane, nitrous oxide in the atmosphere. We have some other proxies too, right? Leaf stomata and leaf shape and whatever else. But we are able to then measure how much CO2 has been in the atmosphere in the past. So the highest previous concentration in CO2 that we've had in the last, say, 800,000 years is on the order of 300 parts per million. In 2017, we were over 405, and as I'll show you in a few minutes, we're now over 415 parts per million. Leaving the kind of modern stuff aside, let's ignore this for a moment. Prior to about, 1880, so like way up here, prior to 1880, all of the climate change that we have seen, right, the fluctuations in carbon dioxide, the fluctuations in temperature, that can be easily explained by natural causes. For example, right, volcanic eruptions, El Nino events, changes in solar energy, and I'll add here too, Milankovitch cycles, right? We're actually seeing fluctuations in Earth's temperature based on the shape of the orbit around the sun. So climate change is a natural phenomenon, absolutely, but the things get a little bit tricky when we zoom into what's been happening recently. If we look at recent changes, right, the observed line here is the black line. The observed changes that we've seen, and now we're showing temperature, it can't all be explained by natural forces. What I mean is, look at the shape of the black line, right? The black line kind of does this. If this was all due to measured natural forces, right, volcanic eruptions, El Nino events, changes in solar energy, the line should look something like this blue envelope down here. So you'll notice there's now a big difference between the blue line that I just drew and the black line, which is the observed data. The only way that we can make the observed data, right, fit with the natural causes is if we add natural causes plus human influence. So the model that is shown in the pink envelope here is the modeled change in temperature when we add both natural climate change as well as human-driven climate changes. And only after we do that do we notice that that black line now fits very nicely within the pink envelope that explains climate changing based on not only natural forces, but also human forces. So what's causing the change, right? We know that climate can fluctuate naturally, but we also know too that we can't explain all of our recent climate change just by natural forcings. So what is causing the change then? Think back to what we said our three main causes of the energy balance can be, right? Changes in greenhouse gases, changes in energy from the sun, or changes in reflectivity at the Earth's surface. So when sunlight hits the Earth, it can either be absorbed, usually through dark colors like land or oceans, or it can be reflected, right? When it's reflected, this is called albedo. Where is it reflected? It's reflected over places that are covered in light colors, ice. When the heat from the sun, is absorbed, the Earth kind of absorbs some of the solar energy, but it also releases some of that energy back out as heat, and so the planet gets warmer. You might find this to be kind of familiar, right? You might have learned about the greenhouse effect. A quick and dirty example of the greenhouse effect is that here, right, energy from the sun is coming through the upper atmosphere, and it hits the Earth. The Earth's surface is heated by the sun, so some of that energy actually comes back out and heads out towards space. Some of that released heat energy can make it through Earth's atmosphere and gets released out into space. However, more and more greenhouse gases in the atmosphere, so if we kind of pack some GHGs up here, right, greenhouse gases, the more greenhouse gases that are in the atmosphere, they decrease this ability of heat to escape. Think of greenhouse gases kind of like a thermal blanket, right? They block those greenhouse gases from getting out into space, and they trap them instead in Earth's atmosphere. So the greenhouse gases in the atmosphere help trap some of the heat that is trying to escape, and so the planet warms. So if we map the global temperature, right? So you're looking at the bar graph in the background is global temperature. And then we superimpose on that the CO2 concentrations. What we notice is that the greenhouse effect is very real, right? When CO2 concentrations are low, temperatures are low. And when CO2 concentrations increase, right, temperatures increase. So if you relate then global temperature on the left axis to CO2 on the right axis, given in parts per million, of course, what we notice is that temperatures have been increasing roughly since about 1880. And if you remember, right, what's the significance about 1880? Well, that's when we really had the kickoff of the Industrial Revolution, right? And when we really started to burn a lot of fossil fuels and pump out greenhouse gases like CO2 and methane. So this is kind of on the broader scale, right? We're looking at the map of 1880 to roughly, 2010 here, noticing that we've had an increase in temperature along with the increase in carbon dioxide. And if we look at today's levels, and they don't literally have today, but I was able to get the June 19th, right? Here's the June 19th. This is measured CO2 concentrations at the Mauna Loa Observatory in Hawaii. And you'll notice that here we are, literally, right, June 19th, 2020, we are now at 415 parts per million CO2 in the global atmosphere. Remember that we said CO2 hadn't been over about 300 ppm in the last 800,000 years or so. And it's not just CO2 that's increasing. The red line here is showing you that since, back literally year 0 to now year 2010, here shown in this graph, not only are CO2 values going up, but we're also seeing an increase in methane and nitrous oxide, all of which are greenhouse gases. Okay, and you'll notice too that they all kind of seem to have the same inflection point, which is about 1880. So not just carbon dioxide, but methane and nitrous oxide are also increasing, and they seem to coincide with an increase in human fossil fuel burning. Whoops. If we zoom in, that's kind of the historical record. I forgot how we have all these circles on here. Sorry about that, guys. If we kind of zoom in, notice now my dates are 1980 to 2018. This is the breakdown now of the increase of carbon dioxide shown in black, methane, and then nitrous oxide is shown in red, and then these are chlorofluorocarbons as well, shown in the orange colors. And you'll notice too that even if we zoom in to just the past couple of decades, you'll see that we've had since 1990 a 43% increase in the amount of annual greenhouse gases that are being pumped into the atmosphere. 43% increase, that's actually pretty significant just in the last, say, 20 to 30 years. And it's not just localized. We're measuring CO2 daily at the top of the Mauna Loa volcano, the observatory in Hawaii. And it was very interesting that it actually not all places on the globe were measuring those really high CO2 values until 2016. The weather station in Antarctica, right, literally at the South Pole, was the last weather station on Earth not to record 400 ppm. So the rest of the planet was recording CO2 concentrations of over 400 parts per million until the middle part of 2016. Once we hit the middle part of 2016, even then the South Pole was now recording over 400 parts per million of CO2. So greenhouse gases are natural, yes, absolutely, and they have fluctuated throughout Earth's history. This is the same graph, it's just stretched a little bit. Remember I showed you this graph before. Here's 800,000 years ago, right? And here's the CO2 concentrations. And there's those beautiful, roughly, right, 100,000 year cycles that we were talking about earlier. And then if you relate those CO2 cycles, right, here's temperature. Beautiful correlations, right? That when CO2 values go up, temperatures go up. And it's almost a perfect, right, one-to-one correlation with these cycles. Remember though too that even though greenhouse gases are natural, the warmest value we've seen in the last 800,000 years is about 300 parts per million. However, remember that now we are way over that. We are at 415 parts per million, right? And we'll talk about in lab, by the way, what each of these little kind of baby fluctuations is. This is just the daily fluctuations or the seasonal fluctuations that are measured due to plants doing their CO2 absorption photosynthetic thing in the summers and not doing quite so much. So recent CO2 changes in the past have exceeded the natural levels that we've seen in the past, tens of thousands to even hundreds of thousands of years. So something is certainly different, at least in the last 800,000 years, that yes, we do see fluctuations in greenhouse gases, but they seem to be much larger than we've seen, at least in recent geologic history. So where's it coming from? Well, since about 1750, of course, right, the burning of fossil fuels, which produces the greenhouse gases that we just talked about, CO2, methane, and nitrous oxide, have certainly increased the amount of greenhouse gas levels in the atmosphere to the highest that they've been in the past 800,000 years. Now, there's another greenhouse gas that we don't often talk about, but believe it or not, water vapor is actually a very important greenhouse gas. And it was funny when Honda first put out its first electric car or hybrid, I think it was a hybrid car, excuse me. One of the things that they were talking about was that the only byproduct that it gave off was water vapor. And it was interesting because I was actually thinking to myself, well, actually, it's funny, water vapor can actually act as a greenhouse gas as well. Slight aside, but, all of these things, CO2, methane, nitrous oxide, and water vapor, they are produced by the burning of fossil fuels, and it does seem that it is coincident with what we're seeing as the recent exponential increase in the amount of gases that we've seen since anthropogenic, burning of those fossil fuels have taken over. Carbon emissions during the industrial age don't all have to be, though, from fossil fuels. It certainly is an important thing, right? So notice that the burning of coal, right? This is 1 million metric tons of carbon that are produced. So coal certainly, right, produces a lot of the carbon emissions. And so does the burning of things like oil and gas. But if you look at this little thin blue sliver up here, believe it or not, the production of cement actually produces a lot of carbon emissions. I'm not sure if a lot of people know that, and I didn't know this, I had to look it up too, but the reason for this is because one of the things used in cement is limestone. And when you kind of burn or react limestone with an acid, you break it down into the calcium ion plus CO2. And so that CO2 can be given off into the atmosphere just in the process of making cement using crushed limestone. So we have a problem with CO2 and greenhouse gases in the atmosphere. And there is a lot of kind of discussion about, well, why don't we just kind of stop producing greenhouse gases, right? So CO2, methane, whatever. If we just stopped right now, wouldn't that solve the problem? Well, actually, no. The lingering problem with CO2 is that lots of these greenhouse gases have what's called a residence time. So they can actually remain in the atmosphere for hundreds of years. So even if we were able to stop emitting CO2, and methane is actually worse, right? Methane actually has a different residence time, but also a different global warming potential. Even if we stopped producing methane and CO2 right now, our global warming issues, our climate change issues wouldn't stop immediately because there is this residence time, right? These gases will stay in the atmosphere on the order of maybe tens to hundreds of years after we stop emitting them. So there's the residence time issue there. That's certainly one issue that we've got that creates a lingering problem with some of these greenhouse gases. But there's another issue that we have to worry about with especially CO2, in that it doesn't just affect the atmosphere. Remember that gases from the atmosphere can get absorbed into the oceans. And because of that, when you add, right, CO2 and water, you might remember that what you make is H2CO3. H2CO3 is carbonic acid. So as we get more and more CO2 in the atmosphere, and that CO2 now dissolves in ocean water, what we're noticing is that the oceans are becoming more acidic. I'll show you the actual data here. This is essentially showing you over here dissolved CO2, right? So there's in Bermuda, we're seeing an increase in the amount of dissolved CO2, which means that the pH, right, the measure of the acidity or alkalinity of Bermuda seawater is going down. That means it's becoming more acidic. Same thing happening in the Canary Islands, right? CO2 values going up, pH going down. Hawaii, CO2 going up, pH of Hawaii waters going down. So as the amount of CO2 in the atmosphere increases, the oceans are doing a very good job of absorbing that CO2. But when they do, the pH drops and oceans are becoming more and more acidic. This is a huge problem, especially for ocean living critters, right? Organisms that make calcite shells, right? Lots of these little seafood guys, they can't make their shells resistant in acidic water. In fact, their shells start to disintegrate in acidic water. So you're going to start to see ecosystem collapse as we get more and more acidic oceans. Those types of marine organisms that rely on having a calcite shell for protection, right? Or oysters, corals, shellfish like crabs and clams, whatever else, those are going to start to decline significantly because their shells can't survive in a low pH environment. The other problem is that as the oceans are absorbing more and more CO2, the oceans are becoming saturated with respect to CO2. Right now, the oceans are helping the global warming issue because they are absorbing a lot of the CO2 that's in the atmosphere. But as the oceans become saturated with CO2, the ocean's ability to take more CO2 out of the atmosphere actually decreases. The other idea here too is warm water can't absorb as much CO2 as colder water. So the increased temperature of seawater is kind of twofold here. The warmer water can't hold as much CO2, but that ocean water is also becoming saturated and can't hold as much CO2. So the oceans are pretty much becoming limited with the amount of CO2 that they can absorb, and we're already seeing problems with ocean acidification. So of course then the question is, greenhouse gases are normal, yes, and the fluctuations in greenhouse gases are normal, yes, but we do seem to see that there is an increase in the greenhouse gas production that seems to coincide with human fossil fuel burning. We're also then seeing an increase in temperature and then an increase in things like ocean acidification. Can we also say, though, that the change in temperature that we've been seeing on Earth is due to a sun cycle? Several scientists have suggested, well, maybe energy levels from the sun have started to increase, and so the warming that we are seeing on Earth has to do with the amount of radiation that the sun is producing. So yes, energy levels from the sun actually do follow an 11-year natural cycle. So on the average of 11 years, the amount of energy put out by the sun does change slightly. So the solar radiation, right, the actual level of energy put out by the sun is shown in the orange line here. And you can see, right, that it kind of has this 11-year cycle superimposed on it. Earth's temperature, however, is shown in the purple line. And so my question to you is, based on especially what's going on over here, can Earth's temperature change essentially be explained by increased energy from the sun? Well, unfortunately, I think the answer is a resounding no, right? Global temperatures have gone up, but notice energy from the sun has actually gone down, at least in the past couple of decades. So can we blame the sun? At least not for the sole reason for why temperature is changing. Our last thing that we were going to check about was, what about reflectivity, right? Remember we said the other thing that could change how much energy we're going to get from the sun is Earth's reflectivity. When we have a lot of snow and ice, right, covering the land surface, we reflect up to about 90% of the incoming radiation over those areas. This is why when you go skiing, you often get a sunburn, right? Because the sun is being reflected off the snow, and so you're getting a sunburn on your face. So when we have areas that are covered by snow and ice, those snow and ice covered areas can reflect up to about 90% of the incoming solar heat. When you then melt all that snow and ice though, and now you have either water or dark colored land surface, notice that the tables turn, right? The reflectivity, or what we call the albedo effect, right? The reflectivity of the land surface changes dramatically to now where you have almost 94% of the incoming radiation is absorbed rather than reflected. Urbanization also affects albedo. For example, as we cut down forests, as we increase deserts, and as we increase the amount of areas that we have covered in things like black pavement, right? The amount of urbanization, all of this actually affects the albedo to where we actually get warmer temperatures because we absorb more heat. So is reflectivity the problem? Well, reflectivity doesn't explain it either, right? Because actually it's going in the opposite direction. As temperatures are getting warmer, what's happening is our snow and ice pack is actually decreasing, and that means we're actually absorbing more and more of the solar energy. So instead of our change in reflectivity being a good thing, it's actually exacerbating the problem of temperature change, because as temperatures warm, we reduce the amount of reflective albedo surfaces, we absorb more water, and we kind of have this positive feedback to where now we're increasing more and more. In 2013, the IPCC report, right, that's the Intergovernmental Panel on Climate Change, reports that they are greater than 95% certain that humans are the dominant cause of climate change. And you saw on my first slide too that more recently in 2019, right, they're saying that climate change is unequivocal. I don't know why I can't say that. But that it is also too, you'll notice over here, right, extremely likely, at least or greater than 95% certainty that humans are the cause for the increase in temperature, and it's resulting from our increase in fossil fuel burning and greenhouse gas production. So who are the major players? So who are the major producers of greenhouse gases? Up until about 5 years ago, believe it or not, the US was actually the #1 producer of carbon dioxide. Only a couple of years ago did China actually surpass us. So the largest producer right now of CO2 is China. This graphic here is showing you the countries of the world, and the size of the bubble is the amount of CO2 that is being produced. And it's showing you too underneath here, not only the rank, so China is #1, US is #2, it's then showing you the millions of tons, right, of carbon produced. And the arrow is showing you too whether they are seeing a general increase in the amount of CO2 production over time or whether they're seeing a decrease. So China is the #1 producer right now of CO2, and it's noticing here that we're getting an increase in the production of greenhouse gases over time. Notice too, India is actually #3, and it is also on the rise in the amount of CO2 that it's producing. Encouragingly, right, the US is number 2, but notice that we're actually going down slightly in the amount that we are seeing produced. The data are showing that definitely we are seeing the impacts of climate change, and it's not localized, right? This is certainly a global phenomenon. We're seeing higher air temperatures. So many of those reports, right? Highest May on record, hottest earlier spring on record. We're definitely seeing that. We're seeing a lot more droughts, and they're certainly becoming more and more severe. And those are usually found in kind of arid regions. In the tropics, however, you're seeing the increase in storms. That increase in storms is because warmer temps, right here, warmer temps means more evaporation, and the higher evaporation off the ocean is what's creating those storm clouds. So in the tropics, right, you're seeing increased storms. We're definitely seeing changing weather patterns, right? We're seeing an increase in the magnitude and the frequency of big hurricanes and storms like Superstorm Sandy. Our oceans are getting warmer, right? And we're also noticing too that our pH is going down. We're seeing globally that there's less snowpack, and that's a huge problem for people who depend on snowpack for their fresh water. We're seeing melting glaciers and shrinking sea ice, which means that sea level, of course, is increasing. And something that we really don't have time to talk about, but we're also seeing a big problem with in the Arctic regions, is that permafrost is thawing. And when permafrost thaws, it actually releases methane gas. And so, of course, methane gas, right, CH4 is methane. Methane gas is then also a greenhouse gas. It also happens to be flammable. So you might actually see some of these videos on YouTube where there are folks actually able to light gas emissions from wetlands, permafrost wetlands in the Arctic on fire. That's because they're bubbling out so much methane. So you're at about 50 minutes here. If you want to take a break, here's a good time to take a break. Because what we'll do is we'll kind of talk about now future scenarios. What's going to happen in the future as we have continued warming temperatures and climate change. So why don't you pause it right here and then come on back when you're ready, and we'll talk about kind of what's going to happen in the next, 10 years to maybe 100 years. Okay, so welcome back. If you're ready to keep going, further implications of global warming. This is kind of what the IPCC and also the NASA predictions are showing, is that as you see an increase in ocean temperatures, we are going to see ecosystems suffering dramatically. One of the big things that we're seeing right now is coral reef degradation. Corals have this symbiotic relationship with these little photosynthetic algae that live in them called zooxanthellae. And what happens when the corals get warm, right, when they get stressed out, what they do is they expel their zooxanthellae. That means, though, that now they don't have that little symbiotic bacteria that is able to help feed them, and the corals are bleaching and dying. So we're seeing a lot of problems with coral degradation. Warmer temperatures means that we can have algae blooms, and sometimes those algae are not good algae or bacteria blooms. What that tends to do is they tend to deplete oxygen from the surface of the ocean, and so you're seeing things like fish kills as well. As we then keep going with further global temperature changes, we will see increased storms, droughts, and water shortages. One thing you might not think about too is health problems, right? Warmer temperatures usually means that those folks who have respiratory issues, right, COPD and asthma and things like that, certainly are going to have longer seasons where they're going to have problems with breathing issues. We'll see the wildfires as well as loss of habitats, especially in polar regions where, the pack ice and snowpack, where you see polar bears and seals and everything else needing that to survive, is all going away. And so those polar organisms are having a lot of trouble. The decrease in the snowpack means that we're going to have reduced water sources. And as the ice is melting, right, the sea level is rising, But also remember too that when water is warmed up, it actually expands just a little bit. So that will also augment the rise that we see in sea level. So let's put some numbers on some of this stuff, right? How are temperatures going to change in the future? How is sea level going to rise? What are the implications? Well, the implications and the magnitude, right, the numbers are going to depend on how we go forward. What will be our rate of greenhouse gas emissions? There's several different models right now. And so there are models that show if we continue to take our greenhouse gas emission and increase it, if we take our greenhouse gas emissions and stabilize them, or if we take our greenhouse gas emissions and actively start to decrease them. So there's several different models that I'll show you in a minute, and they're all kind of dependent upon what we decide to do over the next couple of years. So how strongly the climate responds has to do with how much greenhouse gases we continuously put into the atmosphere, as well as the interaction between those greenhouse gases and natural influences, right? Say we have an El Nino year, say we have a large volcanic eruption. Those things can then augment what is happening in terms of anthropogenic forcing, like our production of greenhouse gases. The future will also depend on the ocean and the atmosphere. These two bodies are extremely large, what we call reservoirs. Reservoirs are essentially things that hold, right, certain components in the Earth's system. The ocean, of course, is a reservoir for water, but it also is a big reservoir for CO2. As we talked about, CO2 dissolves in the ocean water. The atmosphere is a huge reservoir for atmospheric gases. Therefore, making small changes will take a very long time to see anything in these large reservoirs, right? If we then make a small change in the amount of CO2 that we put in the atmosphere, because the atmosphere is so big and has so much CO2 in it, it will take a long time for us to actually see the atmosphere or the ocean to respond to small-term changes. Here's those predictions that I was showing you. And so what these top two graphs are showing is, let's see, years are down here. So this is 2000 and this is showing you the next century, right? So 2100. And the colored lines, the magenta is if we increase the amount of CO2 emissions. So if we actually have higher CO2 emissions than we do today. This is the orange line is higher emissions than today, but not as high as what's modeled in the magenta color. The blue line is if we actually start to lower, right, greenhouse gas emissions. And the green line is if we stabilize greenhouse gas emissions at about 450 parts per million. Remember, right now we're at 415 ppm. So what we're showing you in these models is here's the carbon from fossil fuel CO2 emissions and in these four different scenarios, and then the resulting change, right, in atmospheric CO2 concentrations. And it should make sense that if we have even higher CO2 emissions, right, there's the amount of ppm in carbon dioxide that we might see by 2100. We could even crest 950 parts per million using this magenta scenario. Notice too that if we do stabilize at 450 parts per million, by 2100 we may end up being, right, at that targeted 450 for even the next century. This is, of course, best case scenario if we can actually stabilize at 450 parts per million. Notice that actually, like I said, we're still at 415, but it will take a lot to change the way that the planet now does things, right? Change the way that humans live in order to stabilize and not exceed 450 parts per million. Here are several different impacts that you would see as global temperatures might change in the near future. This is using relative temperature change with respect to the change we saw between 1980 and 1999. And so this is 0 degrees of temperature change, 1, 2, 3, 4, and 5 degrees of temperature change. And these black lines here are kind of showing you when you would start to see significant problems in each of these different key areas: water resources, ecosystems, food, coastlines, and health. So of course, with 3 or so degrees of temperature change, this is where we're going to see a lot of the big changes happening with water availability on the order of hundreds of millions of people, right, under increased water stress. This also is telling you too the citations of the studies where this came from, so this is not just speculation. It's also showing you too that just between 1 and 2 degrees of temperature change is where you're going to start to see coral bleaching. We're already seeing this, right? Wildfire risks. Up to 30% of species at an increased risk of extinction just with 1 degree temperature change. So you can kind of go through this here and see that, yes, we're going to start to see problems with the food chain, right? Cereal productivity, right? Here, when we just get to maybe 2 to 3 degrees temperature. Increased damage from flooding and storms, right? Just from a couple of degrees. And then, of course, the health influences down here as we get up into 1 to 2 degrees temperature change. By the way, if you have any interest in some of these, I would recommend there's a great movie out. Leonardo DiCaprio's movie is called Before the Flood. That's a really great movie, but there's another one that's, I think, called 1.5 degrees. I'll have to look it up, but I'll put the link for you. Some really good, but these are full-length movies. These are like 50-minute movies, but they're really, really interesting. And they kind of show how just 1 to 2 degrees of temperature change can really start to affect things in multiple different parts of the socioeconomic pathways around the world. In the near future, depending again on the emissions scenario that we use, global average temperatures by year 2100 could increase by only 2 degrees Fahrenheit, but they could increase, again, if we use that really high emissions scenario, global average temperatures could increase by 11.5 degrees Fahrenheit. I want to stress this. This is global average temperature. Does that mean that everywhere will get 11.5 degrees hotter? No. Some places will get colder than that, right? But since this is global average temperature, that also could mean that some places could actually be significantly warmer than 11.5 degrees warmer than they are right now. That would be global average temperature, right, would be on the order of, 8 to 11 or 12 degrees warmer than today. And of course, that depends on what we do with our emissions of greenhouse gases. Global average rainfall will certainly increase. However, it's going to be very localized, right? We're not going to have an increase in rainfall everywhere. It will be localized because you'll have then the evaporation off the ocean, which then creates more storms. But that will only be in the tropical areas. In places where you have currently lots of warm air rising and that warm air getting into the Hadley cells, we already have deserts in those areas. And so there will actually be a ramping up, an intensification of the deserts that are already present on the planet. Storm intensity going to increase, right? The strength of winds associated with those storms will increase. And more of the precipitation is going to be rain rather than snow. And so we, of course, then have the problems associated with flooding. But because it's going to be rain rather than snow, we have to deal with that immediately. We can't pack some of that water away as snowpack and save it for the springs when we can melt it and use it as a fresh water supply. Studies have shown that by the year 2100, as temperatures continue to increase, we may actually also see significant changes to crop yields, right, to agriculture. This is showing you essentially that as we get towards the lighter part of the century, more and more of the percentage of yield is going to be decreased by 50 to 100%. That's the decrease in the amount of crops that will be yielding from annual production. So we're going to see food shortages. We're probably going to see an increase in the prices of lots of foods that will be impacted by our increase in temperature change, right? So you'll see grocery store prices going up as well as at the gas pump as well. Remember too that we said that as temperatures go up, sea level is going to go up as well. And for every about 2 degrees Fahrenheit of warming that you have, there's about a 15 to 25% decrease in the sea ice. And the sea ice, of course, and the ice on land is what's continuing to cause sea level rise. Once again, here's multiple different scenarios of sea level rise over the next couple of years, but up to about 2100, you'll notice that all of those projections do continuously show that we will see an increase in sea level on the order of, right, tens to maybe 10 to 20 to 30 inches of sea level rise over the next, say, 100 years. As sea level rises, there will be lots of countries that are going to be vulnerable to sea level risk. Look at how we've got lots of places here in green, of course, but lots of the places that are showing in red, these are the ones that are going to then just be affected by a couple of meters of sea level rise. Notice the US coast as well as the coast of Alaska, having significant places, right, regional extent that would be affected by just a couple of meters of sea level rise. Here's an interesting correlation, right? Here is sea level rise put into the perspective of here are energy facilities, right? Electric, gas, nuclear, whatever else. And a lot of them are on the coastlines of the US within 4 feet above local high tide. So 1.5 meters of sea level rise would actually flood all of these energy facilities. And you can see that a lot of these energy facilities are really important to very large cities, right? Here's all the Texas and Louisiana cities, big California cities, the Pacific Northwest, and up here, of course, this is the New York City metropolitan area. If we zoom in and think about sea level rise right here, look at New Orleans. I'm thinking about you, Kim, right here. There's New Orleans. You can see that all the places in New Orleans that are colored in red are showing that they are less than 1 meter above sea level. And so with just 1 meter of sea level rise, all the areas shown on this map in red would be underwater. And then areas shown in orange on this map are less than 6 meters above sea level. So if you had sea level rise on the order of a couple of meters, right, 3 to 5 to 6 meters, all this area in orange would actually be inundated by seawater. Here's a GIF that shows a little bit closer to home, right? Here's North Carolina. And what it's going to show you is essentially in increments 1 meter of sea level rise and how much of the coastal plain would be flooded up to about 7 meters of sea level rise. So it will repeat. Here's current sea level. And with just 1 meter of sea level rise, notice that most of the outer banks are gone. Up to 4 meters, 5 meters, 6, and then 7 meters of sea level rise. You see that quite a bit of the coastal plain will be inundated with just 7 meters of sea level rise. Ocean acidification predictions suggest that if you want to go learn how to scuba dive and check out some of the coral reefs, you might want to do it sooner rather than later because corals might be rare by the year 2050. Right now, what we're showing is that in kind of pre-industrial, in the 1880s, the areas that were great, the optimal pH conditions for coral reefs were shown in green. Notice how now, as we go to the 2000 map, the areas in green are now significantly reduced, right? And the blue dots are showing you, of course, where coral reefs were and or are currently. And then as we go into 2050, notice how the locations of where most of our coral reefs are now all going to be in this marginal color, right? The calcium carbonate saturation state becomes extremely low. And so calcium carbonate, things that like corals, are very difficult to remain in the solid state because the oceans are so acidic. So most of the world's coral reefs by 2050 could just be in a pH system where it is very difficult to maintain calcium carbonate as a solid. So if you want to check out your coral reefs right now, it's probably a good idea, right? Because we may see them struggling significantly in the next couple of decades. So I'll just end on this idea of, what are we going to do about it? And this is not a political thing at all. In fact, I don't want to get into who did what or who's doing what, but I do want you to know that the EPA is influenced by whatever governmental administration is currently in office. So during the Obama era, the EPA did propose, and this was supported by Obama and Congress, it did support a reduction in power plant carbon emissions by 30% by the year 2030. So there were lots of people that supported this, but of course lots of people who were against this. Kind of the ideas of the reasoning behind it, the pros of this were that it would reduce coal emissions, right? So it would reduce the amount of soot particles as well as greenhouse gases that we put out into the atmosphere. It would, of course, reduce healthcare costs because we would be mining less coal, we would be processing less coal, and all of that stuff, of course, would help with the healthcare costs associated with like black lung and whatever else. And it would also then help to reduce the natural disasters like mine collapses and whatever else. So these were a lot of the pros behind why this was proposed. However, a lot of people were against this, saying that it would definitely reduce the amount of jobs that we have in this country, which probably is very true, and may also create higher electricity costs because we would have to get our electricity from a different resource. And that while we did reduce our greenhouse emissions by 30%, that may not affect global emissions enough to then offset the reduction in jobs and the offset in higher electricity costs. So interestingly enough, just to remind you that these actually do kind of fluctuate with the governments that are currently in office. Oops, I forget that these things here are still here. When the current Trump administration took over, last year, actually, they cut the emission goals by 50%. So remember, the original goal was to cut our emissions by 30% by the year 2030. And they've now decided that they're going to cut that emission goal by about half by 2030. Hoping the idea, of course, is that that would then give people time to find jobs as well as find other electricity means. But again, of course, it's not going to affect our global emissions by reducing the goal emission cut. There are plenty of EPA initiatives that are out there, of course, right? We are now seeing that there are rules about producing more fuel efficient cars. In fact, I can't remember what the year is, but by a year not so far in the future, all cars have to have a minimum, I think it's 35 miles per gallon. And we can do it. We have the ability to do it. So we can certainly put that into effect. Using more renewable fuels, for example, right? Adding a minimum volume of renewable fuel to our highway gasolines. There are plenty of ways that we can actually take CO2 out of the atmosphere and sequester it. That just means bury it, right? We can bury it in rock reservoirs or bury it in deep wells. There are also plenty of new rules that are coming out for coal-fired power plants and other plants where they have to use something called CO2 scrubbing, right? They actually have to now decrease the amount of CO2 and methane that they pump out into the atmosphere by taking their emissions and extracting the greenhouse gases and then either converting it into something that is less damaging or pumping it into some of these sequestration wells. So there are ways that we can kind of combat some of this on the local level as well as at the state and federal level. And I would encourage you to kind of look at some of these and how some countries are doing some really great things associated with this. And how other countries, of course, are struggling with this. They have huge populations. They have lots of people that they have to, of course, feed. They have to provide water for and provide energy and resources for. So I'm thinking about like India and all that with a very booming population. It's very difficult to kind of impart some of these standards when you've got a really big population. So in order to kind of end today's discussion about climate change, I don't want this to become a political issue or seem preachy in any way, but I like to end just this discussion here by saying that, it's kind of a roll of the dice. Do you know what loaded dice are? Loaded dice essentially, it's a pair of dice, right, that you kind of like play a game with. And loaded dice have a weight in them, and the weight kind of helps to skew the results so that, one number turns up more often than the other. And I like to kind of talk about climate change as a pair of loaded dice. One way to understand the human effect, right, the human effect on climate is to compare it to loaded dice. Is it natural? Yes. Are we affecting climate? Also, yes. So while you can never predict the next roll of a pair of loaded dice, loading the dice skews the odds in favor of a certain number or a certain outcome. So is climate change natural? Yes. But are we loading the dice by doing human affected influences? Well, that's also yes. So we are essentially loading the dice so that we are increasing the odds in favor of a certain outcome. And of course, we're already seeing the effects of some of that. Guys, I'm also going to put up on As You Learn, I have a small animation that I put together about the greenhouse effect and about the residence times and greenhouse gas potential of certain things like CO2, methane, and whatever else. And it's another one of those little Cengage animations. So if you have the time and the interest, you might want to check that out, especially before we do our lab on climate change. Otherwise, I will see you tomorrow for our last lecture on alternative energies.